today I'll be talking about the automated monitoring of ocean floor health and how it is a step towards creating a deep seabed digital twin. So this project was done, it is part of the Turing's Environment and Sustainability Project Grant Challenge, and with collaboration with the Center for Environment, Fisheries and Agriculture Sciences, also known as CPAS. So, with some nice good news, this research was highlighted as one of the top Turing research for the last year, and it was highlighted amongst other high impact climate change AI projects like digital twin for cities and UK energy systems. Also a very good news from our collaborators saying that this has been a game changer for automating tool for this task is a good thing to hear from like the challenge owners and the lead ecologist from CPAS. And let me show you a bit of what we have achieved till now. So we have a Euro V5 classifier which is able to identify with 90% accuracy the types of seabeds that we have in the seabed. We have a classifier, we have tracking systems involved, and we have also done a bit of work on video enhancement, automated laser detection. So these are just words. Let me show you some videos what it looks like. So this is a version where we are comparing the human annotation with our model. So what you can see from this video is that along with what the human annotator does, this also classifies it and gives us a confidence interval score. Same is done for the other type of seabeds. So as you can see, this is a very different environment from the previous video, and still our model is able to adapt to this kind of scenario. Moving on, we have some enhancement videos we provided, and this is a preview of how it looks like. And we have used a CLAHI system, which is a variant of adaptive histogram equalizer, which takes care of over amplification of the contrast. And the enhancement has multiple use cases. First of all, it is able to homogenize the entire data set, which is coming from different sorts of environments, different sorts of cameras and everything. Secondly, it provides better visibility for our human annotators, so that means that we are going to get better ground truth. And finally, homogenization leads to better training. Another capability that we added is the laser detection algorithm, which is basically just edge detection, and it helps us counting seabeds with just between these laser pointers to easily measure how many seabeds are there in a particular area. And let me introduce you a bit of what is seabeds. So seabeds are these colonial animals which are closely related to corals, and they live attached to the sea floor. They are feather-shaped and have horny skeleton. That's the basic thing. And they respond to multiple human interventions like contamination or human waste, fishing, boats, etc. And therefore are a very good indicator of the health of the ecosystem they live in. So if a seabed is healthy, then it tells us the mud habitat that it is in, that habitat is healthy. So the work, this work and the goal of this work is to study the abundance and distribution of seabeds so as to evaluate whether the seabed is exposed to good quality water and is undamaged by fishing gear. So the overarching objectives include, is there a way to reliably localize or classify from the available video footage from about 10 years? And is there a methodology that could be employed so that each seabed is being counted once? And finally, can the video footage be homogenized? So these are the things that our partners the questions they came up with. And they provide, in terms of the data that they provided, we had NEFROP's burrow survey data, which had different lighting conditions, different camera setups, and we had two types of seabeds, which are Burgularia and Peninsula, and we had videos of tracking and some annotations. So in terms of the challenge that I am talking about, it's like the basic challenge that they had was different scenarios in terms of camera setup and lighting. And this is what it actually looks like. So when CFAS, the people at CFAS were using classical machine learning algorithms to work on these data, the results that they were getting for different years and different setups was very different. So they were not able to homogenize a model. So we wanted to use some neural networks to actually homogenize the entire modeling. And this is what we came up with. I would not bore you guys with details, but the training, as you can see from the bottom left, so the training starts from taking on these raw video footage with their annotation, dividing them into different frames so that they become images, and then we provide it with, feed it through an algorithm which is either detection or classification, and when it identifies and spits out an output, then we coalesce them into a video which you have seen. So our seabed detection and classification model is basically a ULOV modified ULOV5 model, and it has been trained on the 27,000 images that we created from the videos, and it provides us with about an accuracy of 90%. So these are some of the detection performances. As you can see, with different epochs, the training set box loss and object loss decreases, which is great. We also have intersection over union loss, which is increasing. That's great as well. And these are good metrics for detection performance. And this one is where our model is detecting what happens over every year for every different type of seabeds, that is Peninsula and Burgularia. And as you can see from this graph, that we have been able to kind of homogenize the data, like our model for different scenarios. So it's almost about 60 to 70% of 60 to 70% of accuracy for all these years. And in terms of classification, we also tried a number of different models like basic CNNs, ResNets, and BTG16, which also gave us very nice accuracies. In terms of seabed tracking, we have used Klahi. So when we provide, not Klahi, but when we provide it with an annotation, we are able to identify the same annotation in different steps of the images, as you can see from this video. So it provides it with an ID which sticks with the seabed for the entire video. So it just does it for once. The next part is the laser detection part again, and this is like how we achieved it. It's like very basic edge detection with some image processing. I'm not going to go much into detail with that. And finally, I'd like to conclude by saying the detection and the classification algorithm based on YOLO-V5 provided outstanding results with 90% accuracy. And in parallel, we tested on several classification algorithms. And we tested on models like ResNet, BTG16, and we got great results for all over the years. And we also provided a tracking algorithm that gave us initial seabed detection, and we could track the seabeds in real time, removing double detection. That is great. And we can use this type of data set for models and data set for real-time tracking when this model goes up and running on the CFAS Endeavour's vessel next year. So that would be great. So it's something that's going to go into the field and going to work like our previous work that was on planktons. But I'm not going to talk about that today. And that's it. Thank you. Any questions?
Just to show us, what was the tracking algorithm you used?
I don't remember.
Sorry. Yeah, maybe I can ask very detailed question. So like which kind of framework you use to tune the hyperparameters in this model?
So for now, the hyperparameters still need to be tuned. I would say this is a very preliminary prototype that we did in like a few weeks, and that's something we're looking forward to do, but we're going to do it in Azure cloud computing because all our data is on that. So that's what Azure has on this. Yeah.
Thanks. Yeah, yes.
Sorry, I might have missed this. Why would we want a digital twin?
So, in order to just see how the health of the ecosystem is there, like how it's going, is it going bad over the years? We want to know whether what the parameters are, and that's why we want a digital twin to just monitor that all over the time, so that we could just know the degradation over time.
Brilliant, thank you.
Okay, then thanks Meghna again for the nice talk. Let's move on to